Alright team, I'm going to try to go through this as quick as I can. Definitely review the lecture videos on color vision, and then there's 2 chapters in the Schwartz textbook that talk about this. I'm going to be pulling some of the images from there. As we walk through this lab, I might come back and scroll through this lab a little bit and talk about it. These are kind of cool. These are called Varinator glasses, and essentially they have like a green tint to them when you see them, and they're going to simulate color blindness, a red-green color blindness. The other thing that you might want to get is this app right here. You can play around with it in lab. It's not perfect, but it can simulate the different types of color blindness using the camera on our phone. So I would recommend getting that app. It's free to download. Okay, so let's talk about, for me to understand color blindness, I need to start with the classification of it. And there's really, color blindness, you have 3 types. Well, I'm going to talk about, you can either be a monochromat, so that meaning that you have only rods or only S-cones. I mean, you really have S-cones and rods, but you have no color vision. So when we say monochromat, or we can say achromatopsia, in contrast, we can be a dichromat, where we have 2 color cones. And that is essentially saying that we're missing 1 color cone. And so there's 3 types that we talk about. We have protanopia, deuteranopia, and tritanopia. In this lab, we're going to just pretty much refer to them as just protans, deutans, and tritans. The nopia means there's no cones at all. So in this case, there's no S cones. Oh, sorry, there's no L cones. In this one, there's no M cones. In the tritanopia, there's no S cones. In a little bit difference is you can be a trichromat, would be like a normal person with normal color vision is a trichromat, right? They have 3 different color cones. But if you have an anomalous trichromat, you can be protananomalous. That meaning you're not missing all your L cones, but you're just missing some of the L cones. And then you could be missing some of the M cones. Call that a deuteranomalous. And I can't even say any of these words. And then tritanomalous would be missing some of the S cones. So as we talk about the prevalence of these things, I pulled in, you can kind of look at these at your leisure from the textbook. But we say in general, this is wrong. Let me fix this. Males, about 8% of males have color blindness. So that's 8%, or you can say 1 in 12. For females, the amount of colorblind females that we'll find is about 0.5%, and that's 1 in 200 will have it. And I like this table here, and this is more important for the exam, not so much for the lab quiz, just because we just kind of getting the basics down, but you will be tested on this for the exam, is as you break down the 8%, it all goes here. So that's 1, 2, 3 plus 5 is 8. So that's 8%. And as you really look at that, I mean, if you add up the deuteranomalous with the deuteranopia, that's 6%, or 6 out of that 8. So really, 2/3 of them are deutans, and 1/3, right, protanopia and protanomaly, are protans. So 1 in 12, or 8% of males, are colorblind. 2/3 of those are deutans, with the majority of them being deuteranomalous, and then 1/3 of those being protans. Right, half of those being protanopia and protanomaly. So looking at the prevalence, this is helpful, and we definitely talk about this more in the lectures as well. I included these from the textbook, so this is just showing, for example, a protanopia, how they're just missing that L cone, so it should be about there, right? That would be the L cone, they're missing that. Some things as we get into color, We can describe color with hue, saturation, brightness, and we're going to be using the CIE chromaticity diagram. And this diagram shows the hue, so like the color, right? You see all these different colors, blue, so red, violet, blue, cyan, green, right? And then saturation, so it changes the saturation as you go in and out. What this doesn't have is it doesn't show the brightness, so it's really only a two-dimensional thing of color, but still useful. And we're going to use it in here. This was created, I can't remember, early 1900s, I think, but it was created as a way, and they mapped out color perception of people, of humans, and this is what they came up with. And it really mimics more so the additive colors table, right? And so what you can do is you can look along, if I start at the red here and go all the way down to the green, well, in the middle there is yellow. So if I add in red plus green, I get yellow. So this is talking about light and how we see light. Okay, I added this in just for my notes, just comparing subtractive colors versus additive colors. So we're talking more about this today. Okay. Some things that are also important for this lab, I just want to remind, this is something that you're going to want to know for this lab, is the types of illuminants. So when we look at this CIE chromaticity diagram, they call it, Planckian locus, right here. And this just shows the different illuminants. So you have illuminant A, B, C, right? C is more that white light, that colder color, whereas A is that warmer color, incandescent bulbs. Illuminant B is fluorescent bulbs. And so what we want to do when we're testing color vision is we want to be using as close to white as we can. So we want to be using illuminant C. You definitely want to know these numbers here, that illuminant C is 6800 Kelvin, right? And you want to know these numbers as well. And we want to test with illuminant C. Some of our lamps don't have illuminant C, right? Like if we're in our clinic lanes, we'll have maybe incandescent or fluorescence. So you can use filters we can put on glasses, and you'll see that in lab, and Dr. Kundart will show those to us. The Macbeth easels, I think they have illuminant A, but then it has a filter that takes it up to illuminant C. Okay, so just pay attention to that. You're definitely going to want to know that and those numbers. Okay, those are important for this lab. Let's keep going. Some important numbers. This is one of his slides. I think it's on the next exams material, but he did it as a review. An important thing is knowing that yellow is at 578, and that transition from blue to green is at 495 nanometers. So you're gonna want to know a lot of these nanometer distances or wavelengths. Those are helpful. As we look, I took this from the pre-lab, and I really like to put it with the ones from the textbook, so I put them there. So we need to talk about what you need to know for the lab is you need to know what we call copunctal or black points and the white points. And you need to know this for each different scenario, for a protan, for a deutan, and a tritan. And so a protans, what they mean by a black point or a copunctal point, this is the point where all the lines where they confuse colors converge. So as we let's look at a protan, for example. All the colors on this line here look the same to this person, to a protan. And as I take all those lines and put them all together and they converge on one point, we call this the copunctal point or the black point. So they're going to see this color, which is 700 nanometers or red, as black. Now if you take that copunctal point and you go right through the middle of the white, we call this the white point. So they're going to see this color as white. And if you notice here, this is 490, that's 500. So right here, where's that white point, is 492 nanometers, which we call a greenish blue. So you're going to want to know the black point, the white point. You need to know the wavelength and the color we associate it with, and then the same for this, same for the white point. As we look at a deuteranopia or a deutan, this one's kind of weird. We call this like the extra spectral plane. And so over here is, we're going to call it extra spectral purple. You can just say purple. And we call it like a minus 498. And the reason we're doing that is if we go from this black point through that white point, it takes us to 498. So we don't really have, this number doesn't really exist on the thing, so that's why we're going to call it minus 498, because it's the opposite of that white point of 498, which is a bluish green. Okay, so more on the green side. Remember, 495 right there is the transition between blue to green. So you want to know those. For a tritan, if you look at their black point is at 380, which is violet. And their white point, if you go through the white, you get to yellow, which is 569 nanometers. Okay, so those are really important to know for this lab. Okay. We're going to be using, if you look in the lab manual, it talks about, okay, what are filters going to do? And you definitely try this and see what it does. And those varienator glasses we talked about that are going to simulate. Let's see if I can find it. These things here, these have like a green tint to them. And so they're supposed to simulate what it looks like for color deficient people, and particularly red-green. So that's why I put this here, green, ooh, that's what, eraser. Green filters give a red-green defect. And interestingly, if you have someone that's a protanopia or a deuteranopia and you give them red filters and you're doing like color vision testing with those books and you give them red filters, they'll be able to start to see the numbers or the shapes in there. So red filters can help people with a red-green color blindness, but what does it cause? It causes a tritan defect. So when you put on the red filters or like a red lens, it's going to cause a tritan defect. So it may help a little bit with the red-green color blindness, but then it causes a different problem. Okay, so that's important to know for this lab. This is courtesy of Kate Cooper. This is using that app that we want you to download, and this is from the textbook. So this one shows the normal range of color perception of someone that's normal, or normal trichromat. But if I'm a deuteranopia, you'll notice you can even look at my white point. Look at my white point, right? My white point's that greenish blue, 492. But they don't confuse blue and yellows, but they lose a lot of their red and green, so they can't tell red or green. And so you can kind of compare that here too. So this is kind of how they would see this color spectrum. They see it like this. And then deuteranopia, remember it's similar. The white point is a little bit higher. It's that bluish green at 498. Tritanopia, their white point is yellow, right? 569 yellow. You can see that right there. So they can see greens and reds really well. Yeah, so you can kind of see that. This is kind of cool just to kind of see. You can kind of compare all the colors that they can and cannot see. And it's important to know for the different types of blindness. Remember which of these are X-linked. Well, these two here, red-green color blindness. What colors are they going to be able to see easier? So they can obviously tell all the blues and all the yellows from each other. Red and green right here, those become really hard. Those all blur together. Orange is kind of hard. But anything down here should be good. Like they should be able to tell violet from blue, right? Because those are the kind of different shades of blue and violet. Okay, so that's important to know. As we look to some of the different color vision testing and books, there's a variety of ones, right? We have the Ishihara plates, we have the PIP, which I can't remember what it stands for. But as we look at these types of plates, you have vanishing plates. That's your classic one where you ask them if they can see something or they can't. You have transforming plates, where if you really look close here, this it's supposed to be 74, right? But this 4, because it's got some different colors there in that green, it actually changes to a 1 for someone with a slight defect, red-green color blindness. Hidden plates, the idea with those is only someone that's color deficient will actually see a number. And then diagnostic plates. And this is the basis for the HRR, Handy Riddler. Actually, I have no idea what it stands for. You should know the name. It will help you because, yeah, he likes to put that in the exam, right? Like the full name of things. So just make sure you know what the name of these tests are. This is the foundation for these style here. And the key here is that white and black points get hidden whenever they're in a gray background. So what do I mean by that? So let's look at this page, this slide here. So this 2 is actually a red color, okay? And it's talked about right here. So the red color, remember, you need to remember what your black points are and your white points are. We talked about that the red is the black point for a protan, okay? And it's important to know that the black points and the white points get hidden in this like black and grayish and whitish background here. So a protan will not be able to see the 2 at all. That's going to be completely hidden, and they'll see the 6. And then the opposite is true for the 6. The 6 is, it may look like a pinkish or reddish. It's actually purple. Okay, and that matches up with our black point. Is an extra spectral purple, minus 498 for the deutan. And the deutan will not be able to see this at all. And they will only see the 2. Okay, so that applies to a lot of the testing with the HRR test books. And this is a favorite of Dr. Kundart's. And is honestly the best one out of all the flip books because it can quantify protans, deutans, and tritans. I'm going to zoom into like the scoring table. You can see that we'll go through the details of this and make sure you're comfortable with it. But it does demonstration plates, and then it shows all the symbols, make sure they know all the symbols. Then it's going to test for tritan defects, like large ones, and then deutan defects and protan defects. Now, if they pass that, they're good. Like you finish here, and they have no defects, you're done. But if they fail one of these sections, then you need to go look at these here and see if they have any red-green defects, right? If they fail to here, then you're going to go straight down to here and test for a tritan defect. I will also mention while I'm looking at this that the deutan will see the triangle and the protan will see the circle. Right, the deutan will see the X, the protan will see nothing. So as you're going through lab, that might help you understand and figure out, okay, what should they be seeing? Okay, and that'll be more important for in the proficiency. You're going to say someone with a certain defect is going to be able to see these certain things. Okay, so we'll cover that as we're prepping for proficiency. So as I look at some of these plates, I pulled down the summary of all those black points and those white points to help you here. And as I look at this plate here, so these are the ones from the pre-lab, and he will talk about them again in lab, but I'm putting them here because I remember how confusing it was when we're going through it so fast and having no idea what's happening. Is you have to really look at these and know what color they are. If you know what color they are, you can kind of work backwards knowing the black and the white points to see what they're going to be able to see and what they're not going to be able to see. So this plate here is, we're going to call this, it looks pink, we're going to call it red. Okay, that's the better answer. This here is purple. So the protan, remember their black point is red, so they won't be able to see that, but they'll see the purple. Whereas the opposite holds true for the purple, is the deutans won't see the purple, and so they'll only see the triangle. Okay. And the same holds down here and here. Okay, those are similar plates. These middle plates here are actually tritan plates. Remember their white point's yellow, so that should disappear. Here's another one, violet. Remember 380 is their black point, or violet. That one will disappear. So those are tritan plates. And then here's some more protan deutan plates. Now these look like they're really close in color. We'll look at this one first. We're going to call this one a blue color, and this one a green color. So the blue color, remember at 492, that's the white point of a protan. So they won't be able to see it at all, so the deutan will see it. And then the opposite holds true for the other one. As we look at this one, we're going to call the top one blue and the bottom one green. And really look in lab to see if you can see a little difference. It's hard to see in a picture. But in person, you'll hopefully be able to see that really subtle difference. If you really have no idea, you just go over to the legend, and they should be able to see, this would probably be this one right here. See, the deutan will see the triangle, and the protan will be able to see the circle. Hopefully that matches up. I think it does. Okay. Yeah, so that's that last one. That leads us to the last one, is the Farnsworth and the Lanthony D15. And we're going to be doing the D100 or whatever it is next week. But this one only has 15 different color tiles, and you just put them in order. This is the Farnsworth shown here. And you put them in order, and then you make like a cool graph. Okay. And the Lanthony D15 is the exact same thing. You put them in order, but it's desaturated. So these things are a little bit flawed, and we'll talk about it more in class. But the Farnsworth D15 will miss a lot. It won't detect much, so it's not very sensitive. And then the Lanthony D15, it has too many false positives. So they're both a little flawed, but what's good about them is that they can still quantify if they're protan, deutan, and tritan. So this is, I've included this in here. This shows the different type of defects. When you just trace the, it'll make more sense when you do it. You just trace out the lines, and then you go with whichever one matches the axis. So I think this first one, yeah, this is a protan. See how all the lines here kind of match the angle of this main protan line here? That's all you're doing. So this is a tritan, because most of the lines kind of match that way. And then this deutan, they're a little bit more like this. Yeah, see, they're different. So that's how we're going to go there. As I go back to the lab, I hope that helps. I was trying to go quick because I don't want to take up too much of your time. That should be good. As you go through lab, we're going to talk. You're going to see all these different types of color vision books and charts, and just go through all those, see how they're different, and notice how only the HRR color book really tests for tritans. Okay, hopefully that helps. I'm going to send these slides for you for your convenience. So good luck.